Hello, everyone. Hello, can you hear me? Is everything okay? Can you hear me all right? Sorry, I can't hear you at all.
Yes, we can hear you. They're writing that in chat.
Okay, that's fine. Okay, great. So, first question. The recording of the last lecture, which I have, the previous one, which I have published, is it downloadable? So, did you manage to download it, and is it working for you?
No.
No. So, what is happening?
Couldn't download it personally.
So the file is not downloaded, or it is not playable simply.
I tried to play it, it doesn't play. Try to download it, it's not downloading. Maybe it's only me, I don't know about the other ones.
That's very unfortunate, because obviously, you know, that's the standard MP4 we Zoom produces. So let's see, in case if for whatever reason you can't do that, then I will have to publish slides of this lecture covering the same content as we discussed.
Is it downloadable or not? Like it needs VLC player to be played. Like I couldn't play it with other player.
Because, you know, on my local machine, it was stored, and then I played it in a normal way using just a standard MP4 player, so without any problems.
Okay, for me, it only played with VLC. With other players, it didn't work, so maybe that solves the problem.
Ah, okay, it is only playable with VLC. I presume you have a Mac, right?
No, on Windows, I run.
On Windows with VLC.
Yes.
Interesting. What we can do, okay, so what I can do first of all is possibly convert it to another format and make it playable for you. If not, then I will do slides which would allow you to see exactly the same content as we covered in the previous lecture. Okay. So today we'll continue on the same topic. Why did we introduce the Fokker-Planck partial differential equation last time? Obviously, the answer is we want to compute the transition densities, the transition probability density function, or the probability density function of our stochastic process. Given the initial condition, if you remember, as 0, we want the probability density function at another time, at positive time t, in any point s, which corresponds to some given price at that time. This is a relatively important, I would say very much important task on itself, but there is a big reason why we would like to do this. And this reason in context with data science is going to be discussed today. So today we are covering the topic of estimating the stochastic process, the stochastic parameters, of estimating parameters of our stochastic processes. So let's do a number of simple examples. So I will start sharing my screen, and as before, we'll be using our whiteboard on my computer screen. Okay. Please feel free to tell me if anything is unclear, or you can't see it properly, or you can't hear me properly, and so on. Okay? So, once again, suppose that we have a stochastic process, one-dimensional stochastic process given by a stochastic differential equation, dst equals to some function mu of st and time, And let's say that this function also contains some vector of parameters. I will denote this vector of parameters, let's say by Q. What it is, we'll see in a second. Times dt plus sigma of st and t, which also depends on the vector of parameters Q. Let's say same vector, times dwt. So what could be this vector of parameters? Suppose that for the simple example, we have again a geometric Brownian motion, okay? Geometric Brownian motion. And then you see what these parameters are. So basically, in this case, our function mu of st, t, and q is actually some constant mu bar times st, and our function sigma of st, t, and q is some constant sigma times st. In this case, our vector of parameters q is a two-dimensional vector of real parameters, and obviously our vector q is actually a vector of the parameters mu bar and sigma bar, in which case we assume that sigma bar is positive, whereas mu bar is any. Can be both positive and negative. So the question is, suppose that we have the observed time series of our process. St could be price of a certain financial asset, and because it is a geometric Brownian motion, then you remember which models are described by the geometric Brownian motion. So St could be, for example, an equity, price, or foreign exchange rate. For example, USD ruble. Okay. But we want to know our parameters, mu and sigma. So what do we know about them? Suppose that we have some time series of our process st. We have some values s0, s1, and so on, sn, corresponding to time instance, let's say t0. We can possibly say t0 is equal to 0, but not necessarily. T1, and so on, Tn. That's our time series. So the question is of how to estimate our parameters mu and sigma. Mu bar, sigma bar. Well, in this case, it is relatively simple to do so. You already know, and you remember, that if we solve our stochastic differential equation in this case, so we have SD solution, we'll do it in a slightly more general way as we did it previously. What we're interested in, we have some, for each interval from si minus 1 to fi, we construct the probability density function of si, or more precisely of our s at point ti, conditional on S I minus 1. We already know that log of st, including s of ti, over the initial point, and in this case, the initial point wouldn't be the beginning as t0. It would be si minus 1, the initial point at the beginning of our interval, is normally distributed with the mean equal to, being equal to, you remember, mu bar minus sigma squared bar halved, and the standard deviation, which is equal to sigma bar square root of time difference, the current time t, minus time corresponding to the beginning of this interval, ti minus 1. So instead of considering t0, we consider this particular interval from si minus 1 to si, or from, let's say, ti minus 1 to ti. So t minus ti minus 1. Okay, so this log is normally distributed, as we know. Fine. What can we say then? We can say that this allows us to apply the maximum likelihood principle. MLE is a maximum likelihood estimation. That's what we are going to do. What does it mean? Maximum likelihood estimation. Estimation of what? Estimation of our parameters, unknown parameters, mu and sigma. Suppose that we don't know them, but we do have S1, Sn corresponding to S0, Sn corresponding to time instance T0, Tn. We would like to estimate those parameters. We don't have them. Okay? So what do we do to that end? Suppose that for each interval, the initial point si minus 1 is fixed at ti minus 1, and we have a certain path of our stochastic process starting at that point. Okay, so basically then when si minus 1 is fixed at the beginning of the interval, we assume it to be fixed, at the end of this interval, it is a random variable conditional on the initial value si minus 1. Indeed conditional, because this si minus 1 appears to be in the denominator here for our normally distributed log. So then what we do? We specify any fixed. Is it okay to scroll and to use another screen? Please let me know. Is it okay?
Yes.
Okay, fine. Once again, that's our interval from ti minus 1 to ti. At ti minus 1, we had some, let's say, fixed value at the beginning of the interval, which is si minus 1. And then we have a certain path of our stochastic process, and we have our value s ti, which is same as s of ti, which is a random variable conditional on the initial value s I minus 1. And in particular, the formula on the previous screen was for st for any t, but here once again we would have that log s ti minus 1 over s I minus 1. This is a random variable where this one is considered to be fixed in the moment, is normally distributed with the mean equals to mu minus sigma squared halved, and the standard deviation equal to sigma bar, then let me say tau I, where tau I is the length of this time interval, which is ti minus ti minus 1. Okay? Now, what we do, we fix at this point, we fix some bar or some interval ds, let's say fixed, and we consider the probability of our random variable sti minus 1, sti, a random variable, we are interested in the probability of sti getting into a certain interval from some s to s plus ds. Moreover, for s, we will take the actually observed value si plus ds. So this probability. So si is a constant, it is a really observed value, whereas sti is a random variable, which, well, we know that in fact sti arrives precisely at the value si, right? We know that. But we can't ask what is the probability of this event. Can you tell me please, so what is the probability of sti, which is a random variable conditional on the initial si minus 1, arriving exactly at point si? What is the probability?
0.
0. You're absolutely right. For a continuously distributed random variable, the probability of hitting any particular value is exactly 0. Therefore, this information, if we ask about this probability, doesn't tell us absolutely anything. We can't make any statistical inference or any parameter estimation procedures based on this fact that, you know, STI arrives exactly at SI. But we can ask a slightly different question. If ds is whatever, let's say infinitesimally small, but we would say fixed small value, then we would ask a different question. What is the probability of a random variable, of the random variable sti, getting into this interval from, let's say, si to si plus ds? That's not 0. And moreover, this probability depends obviously on our parameters mu bar and sigma bar. So that's quite easy to say what this probability is. For ds fixed but small, this probability is equal to the probability density function of our random variable sti evaluated at the point si multiplied by the length of the interval ds. Very important point. Is it absolutely obvious that it is expressed that way? Any questions about this? In general, of course, if ds is not small, then this probability would be equal to the cumulative distribution function of STI evaluated at point Si plus ds minus cumulative distribution function. So FSTI is a CDF, which is a cumulative distribution function of the same random variable STI evaluated at the point Si. But for ds being small, we can say that this difference, you remember, FSTI evaluated at the point Si plus ds minus FSTI at Si is approximately equal to the derivative of this cumulative distribution function f prime STI evaluated at point Si times the length of the interval ds, simply by the rules of differentiation. That's how the derivative is defined, right? But the derivative of the probability of the cumulative density function is precisely the probability density function. It is precisely what we denote by FSTI. So indeed, we obtain this. It is a probability density function f, a probability density function of our random variable STI evaluated at a given point Si multiplied by ds. Okay. Moreover, what I can do, this ds may itself depend on the index I. It doesn't need to be same for all I, but again, it is small and fixed. So let us use a more general notation. So let dsi also depend on I. It doesn't really matter. Okay. So now we can ask a more interesting question. Okay, so that the probability of our stochastic process starting at point at time ti minus 1 and a point si minus 1, hitting some interval, but now interval of length dsi from the point si to the point si plus dsi. In general, along the path of our stochastic process, we can make multiple points like that. So again, we start at some S0 at time t0 equal to 0, and we go on and on and on until we have some final time tn. Okay, so then we have a certain path of our stochastic process. All right, then these are actual values. Let's say this is t1 and so on, ti minus 1, ti and so on tn. At each point, there is a certain value of our stochastic process, S1, Si minus 1, Si, and so on. And everywhere, we are asking a question, what the probability is, of our stochastic process, not of course hitting that point exactly. That point S1, S2, and so on, Si minus 1, we already know that this probability is 0. But hitting intervals from that point to, let's say, from S1 to S1 plus ds1, and so on from Si minus 1, as we already know, to Si minus 1 plus dsi minus 1, from Si to Si plus dsi, and so on, from Sn to S n plus dsn. So what is the probability that our stochastic process passes through all those narrow gates in around points which were really encountered, S1 and so on, Si minus 1, Sn, with the size of those gates being ds1, dsn minus 1, and so on and so on. So what is this probability? This probability is, it is actually a very interesting thing. Please watch very carefully how we express this probability. So this overall probability of our path, is equal to, first of all, yes, it is the probability of hitting this interval that st1 belongs to the interval s1 to s1 plus ds1. Okay. Times the probability of, and actually this probability is, let me say, conditional on the initial point s0, times the probability that st2 belongs to the interval s2 to s2 plus ds2. Well, conditional not only on s1, but also conditional on, what does it mean, conditional on s1? More precisely, it means conditional on the fact that st1 equals to s1, but also conditional on s0, that st0 was equal to s0, that we have been in 2 points s0 and s1 prior to visiting our point s2, times so on, times probability that sti any belongs to si plus dsi, conditional on all previously visiting points si minus 1 and so on, s1, s0, which actually means that sti minus 1 was equal to si minus 1, sorry, si minus 1, and so on, st0 was equal to s0, times so on, and a similar probability of stn belonging to the interval from sn to sn plus dsn, again conditional on all previous probabilities from sn minus 1, conditional on all previous events of visiting points sn minus 1 and so on down to s0. Okay, and this horrible expression is actually called the likelihood function of our path from S0 to Sn. This is a likelihood function. Which also depends obviously on our vector of model parameters Q. And in this particular case, if you remember, Q is just a vector of mu and sigma bar. Okay. So basically, this is a probability. This likelihood function is a probability that we, not to say visited each point S1 and so on, Sn, conditional on the starting point S0, but that we visited the neighborhoods of the size ds1, ds2, and so on, dsn of each point, conditional on the initial condition S0, and in general, the probability of visiting the first neighborhood depends only on the initial condition S0. The probability of visiting the second neighborhood depends on the previous points S1 and previous point S1 and the initial point S0, and so on. The probability of visiting the final neighborhood depends on the whole previous history. So it depends on the fact that yes, our process was observed visiting the neighborhood of our previous points Sn minus 1 and so on, and eventually starting at the point S0. That's a very important point. Okay. Any questions about this? Are there any questions about this? Can we go further? Okay.
I think yes.
Okay. So your feedback is important, because please let me know if you don't understand anything, if you don't understand, for example, why we need conditioning on all previous points and so on, then please ask. Why, now I would like to ask you, so why do I need this tower of conditioning that the probability of ST2 passing through this interval is conditional on S1 and also S0 and so on, and the probability of STN passing through the final range from Sn to Sn plus dsn is conditioned on visiting all previous points Sn minus 1 and so on S0. Why is it the case? The probability of this path. Well, this is the case precisely because the fact that our process was observed passing through all those previous points provides extra information about the path. It is not the same thing as just observing our process in, let's say, the final point at time 10, and we know that, let's say, it started at S0 and eventually passed in the neighborhood of the final point Sn. Suppose that we don't have any intermediate information about the path of the process, and the fact that we do know that the process was passing through, let's say, the neighborhoods of the intermediate points before finally arriving at the neighborhood of the point Sn. The fact that we do know all this, it provides much more significant information about our process. So each new probability is evaluated given the information that we know where our process has been previously. So in general, this tower of conditionings appears to be a big, I would say, computational challenge, so we would probably need to compute all those probabilities. Fortunately, in the case under consideration, these probabilities, which being multiplied by each other yield the likelihood function, can be simplified. So I'm turning to the next slide.
One side question, please.
Sorry, what was the question?
one-sided question. Like if ST was a stationary process, then we would not need this kind of conditioning, right?
A kind of. You are right, but in general, you are right. But the problem is that ST by itself is not a stationary process. Indeed,
Okay, I'm just making sure that I understand the read.
but you are right. So if ST were a stationary process, you are completely right. Then the probability distribution of this process at any time absolutely doesn't depend on where this process has been previously. Correct? So, by the way, a very good remark. For a stationary process, ST, you are right. We can say that the probability of, let's say, for any I, the probability of STI belonging to the interval Si to Si plus dSi conditional on the previous points S0 and so on Si minus 1 would in fact not depend on this, and it would be some probability which is a function of, let's say, some probability which is a function of Si only times dSi. In reality, our process given by the stochastic differential equation, in reality, St given by, remember, given by the stochastic differential equation, dst equals to mu bar of, sorry, mu, not mu bar, mu of stt and parameters q dt plus sigma of st t q dwt is not stationary, but it still has a very important and good property, but it is Markovian. A Markovian process in this case means that this probability is not a function of Si only, but it has a limited memory. Or better say, it has no memory at all, apart from the last observed point Si minus 1. So in fact, although this simple formula doesn't hold, unfortunately, but we have another formula which does hold. So this probability is actually a function of this point Si, the previous point Si minus 1, well, it may depend on Ti as well, the previous point Si minus 1 multiplied by dSi. So Si minus 1, yes, it does appear. The last previous observed point for our stochastic process before it arrives in the neighborhood of our point Si. But no dependency on S0 and so on Si minus 2. That's true. And also, obviously, this probability also depends on the vector of our parameters Q. But regarding the path, it only depends on the last point Si minus 1 before reaching this neighborhood of S, the interval from Si to Si plus dSi. So yes, the process is not stationary, but the process is Markovian. For example, if you remember from our previous example that in the geometric Brownian motion case, we have log of S Ti over Si minus 1 is normally distributed with the mean being mu bar minus sigma squared halved. In this case, mu bar minus sigma squared halved times the length of our interval t to I, where to I is Ti minus 1. Okay? And the standard deviation being sigma bar square root of to I. Okay? So in that case, what do we say? We can say that this probability P of Si to I is given by, you know what, conditional on the previous point Si minus 1 is equal to 1 divided by the square root of 2 pi under the square root we would have 2I as well. Outside the square root we have sigma bar. Exponent of minus 1/2 in the denominator sigma bar squared to I. In the numerator we would have Si, the point at which we evaluated, minus what we would have in this case, we would have this log of Si divided by Si minus 1 minus the expected value, which is mu minus sigma squared halved to I squared. I apologize for my, oh my god, handwriting, and I would probably need to type it in and put it on slides. This is a particular example if we have our log of STI over Si minus 1 being normally distributed. In general, this could be just any probability density function. And now we understand that this probability density function is given by, in general, can be given by the Fokker-Planck stochastic differential equation. In the simplest cases, we can construct it analytically. In a more general case, we would need to solve the Fokker-Planck PDE in order to construct this. Let us make just a very short, maybe 5-minute break, and we will continue from that point on. Okay? Okay, continuing. So, in this particular case, when we have the geometric Brownian motion, this allows us to estimate our parameters, our model parameters, in a relatively simple way. So first of all, let me rewrite our likelihood function. Excuse me, please, everything is okay? Can you hear me? Once again, sorry, is the microphone okay? Can you hear me? But I can't hear you. I can't hear any feedback from you.
Yes, we can hear you.
Okay, because there are big delays. Okay, so for the geometric Brownian motion, let's see how our likelihood function would look like. L of Q, in this case, where Q is, you remember, our vector of parameters, mu bar and sigma bar. What we would do, we would say, so once again, it is the product of probabilities from I equals to 1 to n, the probability of our random variable sti belonging to the interval from s I si to si plus dsi conditional on, we now know, only the previous point si minus 1 and no other points because of the Markovian property. Therefore, it is the product of probabilities from I equals to 1 to n. We do some minor simplification because there is a monotonic log function in this case. It is the probability that log of sti divided by s I minus 1 belongs to the interval from log of s I divided by si minus 1 to si plus dsi, again divided by si minus 1. We wouldn't say conditional on s minus 1 because si minus 1 is already in our expression. Okay, this is the product of I1 to n on the following probabilities. Okay, so what is this probability? We already know that this random variable is normally distributed. So for dsi, log, obviously, log si plus dsi divided by si minus 1. Obviously, log of, we can approximate log of si plus dsi divided by si minus 1. We can write for it as log of si plus dsi minus log of si minus 1, which is expanding this log, taking the first derivative for infinitesimally small dsi. It is log of approximately si plus the derivative of the log, which is 1 divided by si times dsi minus log of si minus 1. Log of, therefore, si divided by si minus 1 plus dsi divided by si. Therefore, it is a log of probabilities of our log of sti over si minus 1 belonging to the interval. Which interval? from log of si to si minus 1 to this one, which is log of si divided by si minus 1 plus dsi divided by si. But this random variable is, we know, normally distributed in this case. So it is a product of I equal from I equal to 1 to n. So this one is normally distributed with, we know, mean being equal to mu minus sigma squared half times 2i, and the standard deviation being sigma bar square root of 2i. And then we get this product of probabilities, which is once again 1 divided by the square root of 2 pi 2i sigma bar exponent of minus 1 divided by 2 times sigma bar squared 2i. The actual log of what is the density at this point, the actual value, which is the log of si over si minus 1, minus the expected value, which is mu bar minus sigma squared bar halved times 2i squared. So that's precisely our expression for the likelihood function, okay? This expression by itself would be problematic to evaluate, but instead of this, we can obviously write the log of our likelihood function, log of L of Q, and then obviously the log of the product becomes a sum. It is a sum from I equals to 1 to n. Log of this expression, so let me put it that way. First of all, it is a log of 1 divided by square root of 2 pi to I minus, let's say, log of sigma, and then log of this exponent will obviously be just the expression under the exponent, minus 1/2 square root of si divided by si minus 1 minus mu minus sigma squared bar half to I squared. So what is this? We obtain this type of expression. So what is it? We obtain this likelihood function. What was this likelihood function L of Q? It was the probability of our path of the stochastic process coming through the vicinities of the points actually observed, S1 and so on, Sn. You remember that, right? So the log of this function, yes, it is the log of the probability of our path of the stochastic process, again, passing through same vicinities. Only one point, sorry. obviously this needs to be, that the length of our interval, it needs to be multiplied further by dsi divided by si. And here, when we take the log, therefore it will be plus log of same expression dsi divided by si. Okay. So again, it is the log of the probability of our path of the stochastic process going through the vicinities of our really observed point S1 and so on, Sn. The parameters of our process, which are precisely sigma bar and mu bar, are not known. Then the maximum likelihood principle precisely stands for what can we say? That the likelihood of our process coming through the vicinities of really observed points. Therefore, we would probably like to choose our parameters mu and sigma in such a way that this either the function L of Q itself or the function log L of Q is maximized modular maximized over the parameters mu and sigma. That's reasonable. So basically we derived an estimation procedure for our stochastic process in such a way that we maximize the likelihood or the log of the likelihood of our path over the space of our parameters. We could not select our parameters in such a way that the probabilities of hitting the points S1, S2, and so on, Sn is maximized by itself. Why? Because that probability is 0, as we found, okay? But we could maximize the probabilities of hitting the intervals surrounding our actually observed points, and those intervals, they have values, lengths of equal to dsi, which are arbitrarily small, but constant. So what can we say from the construction we got? Okay, the values of dsi.
Can I ask a question,
Yes,
please?
yes, please.
When you first wrote the exponent minus and this formula, why did you include dsi?
I didn't drop it, I applied the log.
Yes,
L
yes.
of Q is the these expressions.
Yes, in the exponent, why did you write dsi divided by si?
Plus log, you see, it is a product of 1 over square root of 2 pi to I, further divided by sigma, multiplied by the exponent, multiplied by dsi divided by si. When I apply the log to the left-hand side, it is equal to the log of the right-hand side. The log of the product becomes the sum of logs. So instead of the product here, you see there was a product here. Now instead of the product,
okay, I got it. Okay, so the dsi divided by si is not in the exponent. Okay, thank you.
No, it is not in the exponent, of course not. It is the length of our interval. So you see, it is the probability of this expression of this random variable belonging to the interval from log si to si minus 1 to this log, which is actually same thing, log of si over si minus 1 plus dsi over si. So it is outside it is outside of the exponent, definitely. Okay, and now we want this expression to be maximized. Okay, now you see that some terms do not depend on our model parameters. So for example, this log, it doesn't depend, it depends on the nodes, it depends on the values of tau and tau minus 1 and so on, but it doesn't depend on mu and sigma. So we can drop it from consideration because although it will change the value of the maximum, it does not change the coordinates of our maximum in terms of mu bar and sigma bar. From our model parameters point of view, these are just constant terms which do not depend on our model parameters. Again, this log of dsi divided by si is again a constant parameter in this case. It doesn't depend on model parameters. On the other hand, the log of sigma bar does depend on the model parameters. So I can, from this point of view, I can write that again, log of our likelihood function, which depends on our path and q, I would say just depends on q, is equal to some const which, what is this const? Depends on our nodes ti, si, but not on q. Not on q. Okay? Depends on them, but not on q. So there is some constant minus sum from I equal 1 to n log of sigma bar, okay, plus, because now there is a minus in front of the sum, plus 1/2 log of si divided by si minus 1 minus mu plus sigma bar squared halved times tau I squared. And this needs to be maximized over mu bar and sigma bar in order to find the most likely, we would say, values of mu bar and sigma bar. This is a constant, and then minus some of those expressions needs to be maximized. So eventually we can say that an alternative function, which I denote by L tilde of Q, which is in this case sum from I equal to from 1 to n, and first of all 1/2 we can factor out. Then we would have this sum of log of si minus 1 minus again mu bar plus sigma squared. Oh, sorry, not plus, of obviously minus here. Minus sigma squared halved to I squared plus this term doesn't depend on I, and therefore it is equal to just n times log sigma bar this expression, if the previous one needs to be maximized, then this one needs to be minimized over mu bar and sigma bar. Okay? Well, yes. In order to minimize this expression, what do? We take derivatives to compute the minimum. As yet, it is not completely clear what would be the value of the minimum. So let's compute the derivatives. We would say dl d mu bar. Mu bar only occurs through these quadratic terms. By differentiating, we immediately, you will see it immediately. So it is 1/2 sum from I equals to 1 to n partial derivative with respect to mu bar of this expression, which is log of si minus 1 minus mu bar minus sigma bar squared halved to I squared. This expression doesn't depend on mu bar, and therefore we can continue. Obviously, the derivative of the square would have the factor of 2, which is canceling the factor 1/2 in front. So we have it is sum from I equals to 1 to n. And then we have just log of si over si minus 1 minus mu minus sigma squared halved to I, now without the square, times derivative of the expression under the square with respect to mu bar, and this derivative is obviously equal to minus to I. So this derivative needs to be equal to 0 in the point where there is an extremum of our function, either maximum or minimum, we will see shortly, with respect to our parameter. Okay? Now it is very easy to see what happens here. So basically, from this we have sum from I equals to 1 to n log si divided by si minus 1. We have minus here and also minus to I. Therefore, plus this is a constant expression which does not depend on I, so plus mu minus sigma squared halved sum from I1 to n to I squared. Sorry, and obviously we have forgotten we are multiplying by minus times minus 2I here must be equal to 0. So then we immediately see that we can't determine mu and sigma by itself, but we immediately see that mu bar minus sigma squared halved would be equal to with the minus, this expression goes into the right hand side, therefore it is equal to sum from I equal to 1 to n to I log of si over si minus 1 divided by definitely a positive value, sum from I equals to 1 to n to I squared. So that's the first formula, which provides us not with mu bar and sigma bar by itself, but at least with a corrected trend. What is mu bar minus sigma squared bar half? It is a trend adjusted for volatility. Obviously, this is only an estimation. If we select mu bar and sigma squared bar in such a way that this equation holds, then we make the partial derivative of our adjusted log likelihood function L tilde with respect to mu being equal to 0. We still have the second equation, which is the derivative with respect to sigma bar itself. So let us take a note of this expression, and we will proceed with the second one. What I would like to ask you by first of all looking at this expression, from the physical dimensionality point of view, let us see if we constructed something reasonable or something wrong. What is the physical dimensionality? Just let me put our geometric Brownian motion equation once again. DST equals to mu bar st dt plus sigma bar st dwt. So the geometric Brownian motion we're currently investigating. Okay. So what is S? S is the price, which is expressed in units of price, and let's say the unit of price is dollar. So S is expressed in dollars. What is dt? Dt is interval of time. So it is of dimensionality time. St, which is a factor here, is of dimensionality dollar as well. So what is the dimensionality of mu bar in this case? The dimensionality of mu bar is 1 divided by time. Okay? Time to the power minus 1. Time to the power minus 1 multiplied by dollar multiplied by time yields dollar, as it should be in the left-hand side. A slightly more complex question is, what is the dimensionality of sigma bar? Okay, dwt is a quantity which, if you remember, proportional to, it has the standard deviation or the absolute value proportional to the square root of t. Therefore, we can say that the dimensionality of dwt is time to the power 1/2. Okay, the dimensionality of st is dollar again, and we have dollar in the left hand side. Therefore, the dimensionality of sigma is 1 divided by time to the power 1/2. And for this reason, when we have this expression, you see mu minus sigma squared half. So mu has dimensionality t to the power minus 1. Sigma squared half has the dimensionality sigma itself, sigma bar, is t to the power minus 1/2. And therefore, this one has a dimensionality of t minus 1 as well. So this expression is well typed from the dimensionality point of view, because really its dimensionality is t to power minus 1 over t. So the dimensionality of this is supposed to be 1 over t. in the left-hand side. What is the dimensionality of the right-hand side? Si is dollar, Si minus 1 is dollar again. So this ratio of Si to Si minus 1 is obviously dimensionless. And that's correct, because if it were not dimensionless, then we could not apply log to it. So, but log of a dimensionless quantity is well defined, and it is dimensionless as well. Then it is multiplied by tau I. Tau I is the time interval. If you remember, tau I is simply Ti minus 1. Therefore, tau I has the dimensionality of time. In the denominator, tau I squared has the dimensionality of time squared. Therefore, the dimensionality of the right-hand side is time over time squared, which is 1 over time. So we are correct. You see, the dimensionality of the right-hand side is 1 over time. The dimensionality of the left-hand side is 1 over time as well. Therefore, the estimation for mu bar minus sigma bar squared half, which we obtained, is indeed well typed. Okay? So expression 1 is well typed. Fine. Now we need a second equation which will allow us to determine sigma on its own, and then being able to determine mu and sigma, mu bar and sigma bar by themselves. Okay? Okay. So what would we do? Going to the next slide. We write d our L tilde, which is a modified adjusted likelihood function, over sigma bar is. Now we have this expression, you remember, so it is d over d sigma bar of, you remember we had n log sigma, right? Plus sum again 1/2 sum from I1 to n the derivative with respect to sigma bar of this expression, which is log of, you remember once again, Si over Si minus 1 minus mu bar minus sigma bar squared halved times tau I squared, which is simply n divided by sigma bar, plus again 1/2 is cancelled by differentiating the square, sum from I equals to 1 to n of same expression without the square, Si minus 1 minus mu bar minus sigma bar squared halved to I without the square, times its derivative over sigma. We have the plus sign here inside, therefore it is tau I, and the derivative of sigma squared halved with respect to sigma is precisely sigma itself, sigma bar. Okay? And this must be equal to 0 as well, which means that n divided by sigma bar plus sum from I1 to n to I log of Si over Si minus 1 multiplied, and this doesn't depend on sigma, multiplied by sigma bar, okay, minus mu bar minus sigma bar squared halved times sigma bar, sum from I equals to 1 to n to I squared equals to 0, right? I think that's hard. So by itself, this is a quite complex expression, which you see appears to be a power expression in sigma bar, starting from power minus 1 in the first term and up to the square into the last term. But we already got an expression, so we know that what is this? Mu bar minus sigma bar squared halved from our previous estimation, moreover multiplied by this is precisely this the product of these two terms from equation 1. This product is simply equal to, we know what it is. It is sum from I equals to 1 to n to I log of Si over Si minus 1. That's precisely this. And this is equal to the same term in the left-hand side. All right. Okay. So I can't say that I like it very much because what does it mean? In that case, this derivative would never be equal to 0. It would be equal to n divided by sigma bar, and it would be positive in any case. Let us double check whether it is indeed so. So we have for the original likelihood function. So if you remember, we had for L tilde we would have n. Let's see once again. N log sigma bar plus 1/2 sum from I1 to n squares of log of Si over Si minus 1 minus the expected value, which is mu minus sigma squared halved to I squared, and this needs to be minimized. Okay, let's see, first of all, let's see how this function depends on sigma bar. When sigma bar tends to 0, then what? The first term would tend to minus infinity, obviously, whereas the second term remains bounded. Therefore, in this case, we would say L, our function would tend to minus this function would tend to minus infinity, which I don't really like. Sigma bar, when obviously sigma bar tends to plus infinity, then I think we made an error with the sign somewhere in our computations, because what happens is that when sigma bar tends to plus infinity, we would have obviously log tending to plus infinity as well. And here under the square, this sum would tend to plus infinity as well. So what I don't really like is that in this case, this expression does not look like, you know, it has an extremum point with respect to sigma. ETP is to be arranging when sigma is from 0 to plus infinity. I wouldn't obviously claim that it is monotonic, but the fact that it tends to minus infinity as sigma tends to minus infinity to 0, it means that we did something. Okay. And you didn't tell me. That's all correct, but you remember that I think we lost the function is different. This is a square of this is a square of the difference between the random variable and its expected value, but you remember there is a sigma bar squared to I in the denominator, and therefore it is 1 divided by 2i here as well. Sorry, we will need to, unfortunately, with this, it is not a whiteboard. We would need to quickly redo our computations. What we got is not exactly correct. So our likelihood function is actually it is yes, n log sigma bar plus not 1/2, but 1 divided by 2 times sigma bar squared to I. And you didn't stop me. Why have we missed that? Sum from I1 to n, and then indeed log si over si minus 1 minus mu bar minus sigma bar squared halved to I squared, and this needs to be maximized over mu bar sigma bar. So we missed our division by sigma bar to I. Actually, this would not change anything for the derivative with respect to mu, because when we take this derivative, the first term vanishes. the second term becomes a sum which is equal to 0 up to a constant factor, which we drop. Therefore, the equation 1 still holds. It is still exactly the same. So we would have mu bar minus sigma bar squared halved would still be given by same expression as it stood before, which is from I from 1 to n to I log of Si over Si minus 1 divided by the sum of squares of our intervals from 1 to n to I squared. So that's still okay. But now dl tilde over d sigma is obviously going to be n divided by sigma bar plus now a much more complex expression. First of all, to I needs to be inside inside the summation, and in this case we would have now obviously you understand that when sigma tends to 0, then the second term tends to plus infinity and the first term tends to minus infinity, and therefore we do not have this behavior that L tilde tends to minus infinity. Okay, therefore we have by let's say plus by differentiating the first term, we have I would say just we would have minus 2 times sigma bar cubed times 1/2 sum from I equal 1 to n, same expression Si minus 1 minus mu minus sigma squared halved to I squared 1 divided by 2I and plus now differentiating the square, therefore plus 1 divided by sigma bar squared sum from I1 to n 1 divided by 2I square and 1/2 cancels, log of Si over Si minus 1 minus same expression mu minus sigma squared halved 2I sorry, not squared anymore, times the derivative with respect to first of all sigma squared half, which is 2I itself, times sigma bar itself. Now 2I cancels, sigma bar cancels with its square here, and this must be equal to 0. So what do we get as a result? As a result, we get, so it would be n, it would be therefore 1 divided by sigma bar n minus sum from I1 to n log Si over Si minus 1 minus this expression, which we already know what it is, sigma bar squared halved to I must be equal to 1 divided by sigma bar cubed, sum from I1 to n, and those expressions log of Si over Si minus 1 minus same expression 2i squared 1 divided by 2i. Now we are done. You see, however complex these expressions look like, but in fact there is nothing that terrible about them. This expression for mu minus sigma squared bar halved is already given by this expression, so it is fully computable in terms of our Si and 2i. This expression as well. So basically this term and this term do not contain any unknowns and is completely defined by our points 2i and Si. Therefore, the only occurrence of the unknown sigma is in this factor, which we can cancel, and in this factor, which is now 1 divided by sigma squared halved, which allows us to compute analytically sigma bar halved, and then from that we can compute mu. This precisely solves our problem. But you see that even for the geometric Brownian motion, in the general case, estimating parameters of our process is a non-trivial exercise. We had log normal distribution for our prices Si. We had normal distributions for the log of S of Ti over the initial value at the beginning of the interval Si minus 1. And nevertheless, we got relatively complicated expressions which allow us to estimate the parameters of the model using the maximum likelihood principle. I will put everything on slides in order not to confuse you, because as we have seen, it is quite an involved arithmetic in this case. In the general situation, when we don't have the analytical expressions of this kind, we need to solve these equations numerically using the transition densities functions obtained numerically by solving the Fourier-Planck partial differential equation. We will return to this topic in the next lecture. But for the moment, I think we are done. Thank you. Any questions? Any points which I would need to address? Not really? Okay, if we're okay to finish now, then I will put it on slides for information, as well as trying to put this lecture in a form which you can download, and we will continue from this point on next time. But now it will be the more general case. Instead of the log normal distribution, there will be an arbitrary function which gives us the density of, let's say, Si at point Ti, conditional on the previous point Si minus 1. And we'll try to solve it, or at least to develop numerical methods of solving it in order to estimate the parameters of our model. Thank you.
Thank you. Goodbye.
Bye.